In this lecture, we are going to discuss how we can use convolutional neural networks for sequences, specifically text. Although the type of CNN we are about to discuss will work just as well for generic sequences too. You might be wondering, how can this be? If CNNs are for images, how is it possible for CNNs to also work with sequences? First, let's recall the basics of convolution. The idea is this. You have an image which is the big square. You have a filter which is the small square. And you're going to slide the filter along each possible position in the big square. And at each point, you're going to multiply all the overlapping values and add them together, just like a dot product. Now, I know this is obvious, but it's worth taking note of. An image has two dimensions, height and width. There is also the feature dimension, but that's not an actual dimension which has correlation. And recall what I mean by correlation. If you have a picture of a red car, and you find a pixel in the image which is red, probably the neighboring pixels are also red. In other words, pixels beside each other likely have similar values. Now think of a sequence. Unlike an image, a sequence has just one dimension that is not a feature, time. So it's time instead of space. But notice one important detail. We have the same type of correlation in sequences. Data which are nearby other data in time are also close in value. That's why this appears like a smooth curve rather than just noise jumping around with random uncorrelated values. This suggests that convolution might be useful here as well. Luckily, convolution in one dimension is actually much simpler than convolution in two dimensions. Instead of a big square, we just have a big line, and the filter is the smaller line. Then we slide the small line across every position in the big line, multiply all the overlapping values, and add them together. Let's do a simple example. For the sequence data, we have 1, 2, 3, 2, 1. And for the filter, we have simply +1, -1. As an exercise, you might want to try to figure out the answer first before we move on to the solution. Okay, so here's what we get. At the first position, we have 1 times 1 plus 2 times -1, which is -1. At the second position, we get 2 times 1 plus 3 times -1, which is -1. At the third position, we get 3 times 1 plus 2 times -1, which is 1. And at the fourth and final position, we get 2 times 1 plus 1 times -1, which is 1. So essentially, exactly what we would expect. As with images, it's possible to express this operation as an equation. And remember that in deep learning, while we call this convolution, pure mathematicians and statisticians would call this cross-correlation. So just keep in mind that the sign is reversed. As an exercise, you might want to try and confirm to yourself that this equation does in fact implement the operation we just performed in the previous example. And remember that another thing we can do is add on features. So imagine X as a t by d array, where t is the number of time steps and d is the number of input features. Then imagine the output as another two-dimensional array of size t by m, where t is the number of time steps and m is the number of output features. Then w must be a three-dimensional array, t by d by m, and then we would have the equation that we see here. This is just like convolution with images. For a two-dimensional convolution, we have two spatial dimensions, plus one dimension for the input features, plus one dimension for the output features. So that's 4 dimensions in total. For a one-dimensional convolution, we have one time dimension, plus one dimension for the input features, plus one dimension for the output features. So that's 3 dimensions in total. As usual, While convolution might seem like an abstract concept, remember that there are multiple convenient perspectives on it that make it seem like things we are already familiar with. So one perspective is that it's just matrix multiplication, just like a regular feed-forward neural network, except that we have shared weights in order to take advantage of the special structure and correlation in the data. Another intuitive perspective is that it's just a sliding dot product, and the dot product is just a correlation finder. Correlation is just another name for pattern matching or similarity. So really what we are doing is asking, is this part of the sequence similar to my filter? And thus the filter becomes a pattern matcher or a pattern finder. All these concepts that you learned about convolution before still apply here. Alright, so now that you know how convolution works with sequences, how do we apply these to text? Well, luckily, when we use embeddings, that already gives us exactly what we need. For one-dimensional convolution, we need an input, which is a t by d sequence, where t is the number of time steps and d is the number of features. And of course, this is exactly what we get after we pass our sentence through an embedding layer. We go from a length t sequence of words to a length t sequence of integers to a length t sequence of d length vectors. Since we have t vectors, each of length d, this makes up a t by d matrix when you stack them all together. And thus, we have exactly what we need to build a CNN for text. So here's how it all looks in code. First we have our input, that's a length t sequence of word indexes. Then we have an embedding layer. The output of that is a t by d sequence of word vectors. Then we have a 1D convolution. This is just the conv1d class. Then we follow the same typical CNN architecture, where we have convolution followed by pooling and so forth. So the same pattern applies here that we had for images. Generally speaking, the data shrinks in the time dimension, but grows in the feature dimension. So that's why you see the number of feature maps getting larger and larger. Once we're done that, then we can do a flatten, or we can do a global max pooling, which will give us a single vector of size M3. Finally, we pass this through one or more dense layers to get a single scalar, assuming we are doing binary classification. As you can see, this is no different from a CNN meant for images, except that all the convolutions and pooling are one-dimensional instead of two-dimensional. There's one small caveat to what we just discussed, but it's not obvious until we try to implement the forward function. Inside the constructor, there's no real problem because all we're doing is instantiating some objects. But remember that in PyTorch, the general convention is that for convolution, features come first. We saw this earlier in the context of two-dimensional convolution on images. PyTorch convolution works on images of size n by c by h by w, which means that color comes before the spatial dimensions. In other words, a feature comes first. However, in TensorFlow, OpenCV, and other libraries, we use the convention n by h by w by c, which means that the feature dimension comes last. Torch Vision, in some sense, accepts that this is the convention and makes its interface such that you can work with n by h by w by c all throughout your code and never have to worry about the fact that in PyTorch things are backwards. This is because you don't ever interact with the data explicitly. Torch Vision does all that work for you. But now we have this mixture of conventions. The output of an embedding is n by t by d, where t is the sequence length and d is the feature dimension. So the feature comes last when it's the output of an embedding. But the conv1d function, just like the conv2d function, expects the features to be first. In other words, it expects the features to come before the time dimension. So it wants to see n by d by t and not n by t by d. What we end up having to do is permuting the data right after the embedding and before the first convolution. So after the embedding, it's features last, but before the first convolution, we reshape it to features first. Then, after all of our convolutions and poolings have been done, we permute the data back from features first to features last. At that point, we can pass the data through the usual dense layers that make up the rest of the CNN. So here it is in action. Since there are many layers in a CNN, I've split this up to make it more readable. Here we take in the input and pass it through an embedding layer. Then we do a series of convolutions and poolings. I'm not going to show all the convolutions and poolings since we just repeat the same pattern over and over. But we can reason about the shapes. So first, the input x is an n by t array of integers. After the embedding, it becomes n by t by d word vectors. Next, we permute the dimensions so it becomes n by d by t. After the first convolution, we change the number of features so it becomes n by m by t. The rel u which comes next doesn't change the shape of the data. After pooling, which changes the length of the sequence, we get n by m by t2. You can think of t2 as t divided by 2 or t divided by 3, depending on the pooling parameters. Next, we go through the second convolution and so on and so forth. So let's pretend that we had 3 convolutions. So after the final convolution, our data has the shape n by m3 by t3. At this point, we need the features to be last again, so we call permute again, and we get n by t3 by m3. After doing a global max pool along the time dimension, we get n by m3. Note that because we can specify the axis to perform the global max pool on, we didn't necessarily have to permute the data after the final convolution. You could just choose a different axis. Although I think this makes it more clear what's going on. Lastly, we pass the data through a final dense layer, and as usual, we get back an array of size n by k.